Most people think of their phone storage like a single PC hard drive, but that's a dangerous misconception. Here is what actually happens under the hood. Android storage is more like a highly secured building with dozens of sealed rooms. As you can see from the highlighted text, it's strictly divided into logical blocks. This isn't just for organization, it's the foundation of the entire platform's security and update model. So, why go through all this trouble? The highlighted text points to the core reasons: security, factory resets, and updates. By isolating the core OS from user data and vendor hardware code, we create firewalls. A malicious app downloaded by a user can't infect the core operating system, and a factory reset can wipe user data without touching the pristine OS, ensuring the phone can always boot back to its original state. Let's start where the device starts, the boot partition. Think of this as the key in the ignition. The highlighted text notes it contains the Linux kernel and the initial RAM disk. Its only job is to get the most basic hardware running, find the other partitions, and kickstart the very first user space process, which we call init. Without a valid boot partition, your device is nothing more than a paperweight. Once init is running, it mounts the system partition, which is the heart of Android itself. Notice the contents listed here: the API framework, system apps like System UI, all the core libraries. The trick that took me 3 years to learn is the importance of its mount property. It's read only. This is a non-negotiable security boundary. It means even if an app gains root, it cannot permanently modify the core OS files on this partition. Now this is where things get interesting, especially after Android 8.0. The vendor partition was our solution to a massive headache called Project Treble. Before this, hardware code from Qualcomm or MediaTek lived inside the system partition. This meant a simple OS update required a full driver rewrite from the chip vendor. By separating it out, as highlighted, we can update the Android OS without ever touching the hardware-specific drivers, a huge win for faster updates. Finally, we get to the only place you, the user, are allowed to play: user data. Most people trip over this because they think their apps are installed in system. They are not. As the highlighted text explains, all your downloaded apps, photos, and settings live here. This partition is mounted read-write, which is why when you perform a factory reset, we simply execute a command like make ext4fs on the user data block device. The read-only system partition remains completely untouched. You don't have to take my word for it. You can see this for yourself. Here is what actually happens under the hood when you run the command you see highlighted: adb shell df-h. This command, df, stands for disk free. It queries the kernel and lists all the mounted file systems, showing you the exact block device path, its size, how much is used, and crucially, its mount point, like /system, /data, and /vendor. As Android's complexity grew, even the system/vendor split wasn't enough. We needed more granularity, more isolation. This led to the creation of what the text calls secondary framework partitions. Think of these not as primary building blocks, but as specialized rooms added to the main structure to handle very specific types of code that didn't cleanly fit into the original design, solving new problems as the ecosystem evolved. The product partition is a perfect example of this evolution. It's the designated place for OEM-specific apps and customizations, what some people might call bloatware. By forcing these customizations into their own partition, as the highlighted text notes, we ensure the core /system partition remains as close to pure AOSP as possible. This makes debugging easier and separates Google's code from, say, Samsung's custom launcher. The system_ext partition is a bit of an insider secret. Here is what actually happens. Some system components, often those close to the hardware, need to use private or unstable APIs that aren't part of the public SDK. We didn't want this code polluting the main /system partition. So as you see highlighted, system_ext became the designated home for privileged modules that are not quite AOSP core, but are more than just a vendor HAL. You might also see an ODM partition, which stands for Original Design Manufacturer. Most people trip over this because it sounds just like /vendor. The key difference, as the text implies, is scope. /vendor is for the silicon vendor, like Qualcomm. /ODM is for the device manufacturer, like Foxconn, for board-specific drivers or configurations that are independent of the main SoC. It's another layer of separating responsibilities. Finding the actual block device for these partitions can be tricky because the names can change. Slower now, the trick that took me years to learn is to use the symbolic links in /dev/block/boot device/ by name. The highlighted command shows this perfectly. Instead of guessing the device name, you list the contents of this directory and the kernel provides a stable human-readable name like vendor that points to the correct underlying block device.
Now let's connect this all to something you experience constantly: over-the-air updates. The partition layout is not static. It dictates the entire update mechanism. The highlighted text here introduces the single most important innovation for updates in the last decade, the AB partition scheme. This fundamentally changed how we deliver new versions of Android to your device, making the process nearly invisible to you. So how does it work? Instead of one system partition, we have two identical slots, A and B. As the text explains, if you're currently running on slot A, the OTA update is downloaded and written directly to the inactive slot B partitions in the background. When you reboot, the bootloader simply flips a switch to make slot B the active one. This makes updates incredibly fast and provides a perfect fallback if the update fails. We just boot back to the old working slot A.
Enjoyed the video? Hit like and subscribe for your regular dose of AOSP customization. Thanks for watching. See you in the next one.